vertex WS. And so our motivation is just, first of all, there is a duality because the upper bound dtws, which implies upper bound on dtuv. So the motivation is that we want to upper bound on expectation of dtws u and v. And we can say that without loss of generality, the distance between ws and u, this distance, is less than the distance between ws and v, this distance. So it belongs to the right cluster. And if center ws cuts u and v, it means that the distance between ws and u is less than beta I, which is less than distance between ws and v for some level I. And ws settles E at level I. And so we can say that 2 to the I plus 2 is less than 8 beta I, because we would love to cut at lower levels, we're bounding I, and this is greater or equal to your ws distance between u and v. And as you read this article, you will see that, for example, if x in distance between omega s and u and distance between omega s and v, if it is in this interval, then from the observation 1 that is mentioned in the article, you can see that the probability that beta I lies in x and x plus dx, because we hate this to happen, so we want to minimize and reduce it. So this one is less than x ln2 dx. So any of w1, w2, w1, it could be ws, any of them can settle u and v at level I. But we first pick the first one. We pick the first one. The first one amongst those in permutation will then settle u and v. And so here we can say that the probability that ws settles E at level I is at most 1 over s. Any of them could have, because we have s of them, so any of them could settle. And so we can say that expectation for our ws dt distance metric is less than, so we find the integral, which is between ws and u, and x could be ws and v. Because the probability is x ln2, and it is less than 8 beta, so 8x. And I've just told you that 1 over s is the probability of that selection. So in overall, you can write, so this one, this is less than 2 to the I plus 2, and this is less than 8 beta I. And that's why 8x, this is less, so this is upper bounded by this one. And this is the probability, and this is 1 over s, the probability of settling E at level I. And if you simplify this, it becomes 8 over s ln2 d of ws minus v minus d of ws minus u. But you know from triangle inequality that this is less than d of u and v. So we have done it for just one WST metric, that expectation of dt, ws, u, and v. Until now, we have proved that this is less than the distance between u and v and SLN of 2. But you know that we can use linearity of expectation because we have shown you that the distance between u and v is less than the distance between u and v, and just take the expectation. So expectation of this is less than the expectation of this, and I've proved from here that this is less than 8, so this one goes here, 8 d of u and v over SLN2. And this is less than log n. You know, this one is less than log n. And so this becomes 8d of u and v over ln2. So it's sublinear and less than 8 ln of n over ln of 2 d of u and v, which is equal to, you know, this one is log of n. So this becomes 8 log of n, distance between u and v. So we conclude that for any edge u and v, the expectation of the tree metric, distance between u and v is of order of log n times d u and v. So the distortion is order of log n, which is very nice. It is much better than 1996 paper of, or 1995 paper of Bartol expectation. I mean, the distortion was log n, I guess. I don't remember. But now it is much more or something worse than that. But now it is just order of log n, which is a tighter approximation, and it is much better. So this approach is quite probabilistic, because first you had permutation, saying that, for example, you arrange your vertices. Second, you choose beta and from an interval and multiply it by some number. And beta could be anything, so this beta I could be anything. So this makes another source of, this is another source of randomness. But in the next lectures, I start by introducing a deterministic approach for embedding any metric into a tree metric. And the tree that we are interested in is just low stretch spanning tree that is popular in computer science. And spanning tree has some good properties, but the cons of that, it has some pros and cons. The disadvantage of using low stretch spanning tree is that it is restricting us. So we cannot control some measures and our distortion grows. But here I like this approach, which is probabilistic. I mean, the work of Talvar that I've just explained. Because first of all, it is probabilistic. You have more source of redundancy, let's say, that you have more control over different possibilities. Because, for example, when you say this one, and all of these trees are answers, Each tree is good, has a good distortion for a set of points. This tree is good in some cases. It's good, and so if you take average, you get a good and low distortion. But if it is fixed and deterministic, especially if it is a spanning tree, then everything is rigid. You cannot do anything you want, because you have everything is very rigid and deterministic, and you cannot do anything. But the work of Talwar is very inspiring for me, because first of all, you can use all of the ideas from set theory, because you're doing it probabilistically. And second of all, you will see that it is more natural to think about graphs as something that has less structure on that, in order to create more natural theories and have lower distortion. Even in this algorithm that I explained, in the first step you do some permutations, but how you want to make a structure on that is an issue. You can develop more algorithm. Also, your beta could be, you can create a Markov process, and you can use many of the ideas, martingale, many of the ideas of probability theory in this framework. So this guy wrote an article which is very fundamental, and it is in 2004, but it is I mean, people will use it in future, because it is one of the most successful approaches for embedding into a distribution of a tree. Not just embedding into a tree, not just embedding into an ultrametric. And it is more natural than many of the approaches. And we can also combine different algorithms using this paradigm of the work of Talwar. And Talwar is now, as I said, is in Microsoft working on differential privacy. And I've seen that his articles are not related to metric embedding anymore, but he is a pioneer in this field. In the field of course, Bartol formalized this probabilistic partitioning, and Bartol, Abraham Itai, and Itai Abraham. So this guy, and this guy. So these three guys are very genius, because they are the first people who introduced probabilistic partitioning. And so maybe they are inspired by guys like Erdős, who use probability and random processes for graph theory. Because if you create a random process, you will see some connections between some very classical ideas in graph theory and computer science and analysis. And so that's why randomness creates a fruitful area of research and is very useful. I mean, many of the algorithm in Microsoft is currently under this idea of random process, and creating a graph and working on graph based on these ideas of Talwar. Oh, maybe that's why Talwar is working in Microsoft. And so in the next lecture, I will talk about petal decomposition with the work of Itai Abraham. And in the petal decomposition, we want to build a low stretch spanning tree. And of course, that work is inspired by the work of Mikhail Elkin in 2005. which is a lower stretch spanning tree algorithm, and it uses star decomposition. But later, Itai Abraham looked at his algorithm, so that's very nice. So he improved that algorithm and kind of reducing some sources of uncertainty, and he had better control over the distances when he's growing their petals. And so the work of Itai Abraham is inspired by, I think it is inspired by the work of Mikhail Elkin, because their algorithm is quite similar, very, very similar. And but it is a modification of the algorithm, because in the Mikhail Elkin paper, he talked about the star decomposition. He said star decomposition, not petal decomposition. But they are essentially the same ideas. And the innovation of Itai over Mikhail Elkin article is that it has an optimal control and the radius increase of spanning tree. So, for example, it increases by at most a factor of 4 over all recursion levels, which is quite an improvement. And so you have two sources. So you have seen in my lectures that we first embedded into R, then we embedded into LP, and then in this lecture we embedded into a distribution of trees. Some people embedded into trees. Some people embedded into ultrametrics. Some people embedded into, like next lecture, into a low stretch spanning tree. Don't forget, spanning tree is not expander. Expander is something else. Both of them are quite popular in computer science. And so distribution of trees, this is probabilistic. And most of the algorithm on embedding into trees are deterministic, but I like probabilistic way. And so you can embed it even into some other structures, very complicated structures, such as snowflakes. It's like fractal. You can embed it. So the theory of metric embedding is so vast. And you can use it for dimension reduction in machine learning. And I predict it is the future of dimension reduction in machine learning, because it doesn't have a restrictive structure. You can develop everything naturally. Just like MySQL is dead for graphy data, and some people use, my favorite is Neo4j, because when the type of your data is graphy, then you can avoid lots of joins in MySQL. And so Neo4j can scale your business if you have any problem, from healthcare, from algorithmic trading and finance, any problem. You can scale your business with Neo4j. So you should hire people who know Neo4j. And of course, you can connect it to Kafka for streaming, GraphQL, REST services. And so Neo4j is a really good approach to graph theory. Of course, you should develop and write lots of Cypher codes and Python codes to be able to integrate machine learning with graph theory. And that is the state of the art, because even very few companies are doing that. One of the great companies that are doing that is Tiger Graph. This company is in California, I guess. It is a really good company. It is active on the intersection of machine learning and graph theory. But it's just the beginning of these